This is section 15.6 on triple integrals. So some of these can get really long, as you might guess. Right, so page 1029, 15.6, triple integrals. So we're integrating over a three-dimensional region. The simplest case is over a box where x is going from one constant to another, y is going from one constant to another, and z is going from one constant to another. Typical slice, you have a delta x, delta y, and delta z, naturally. So you might integrate over a region, and you chop the region up into so many pieces. Right, so on page 1030, we have Fubini's theorem for triple integrals. If f is continuous on a rectangular box, AB, that's for x, cross CD for y, cross RS for z. Okay, this is not a cross product. This is the limits for x, y, and z. Then the triple integral over some box B of f of x, y, z, dv. So basically dv is dx, dy, dz in some order. Okay, Fubini's theorem says you can switch them around any way you want. Dz, dy, dx is actually going to be our quote unquote favorite. I mean, right now we're used to having z as a function of x and y. And then after that, we like y as a function of x, and then x comes after that. Okay, there's actually 6 ways you can arrange these three factorial formally for you combinatorics people. But the basic idea is how many ways can you have the first letter? Well, 3. You can have either dx, dy, dz. Once you put that one down, there's 2 other choices. And then once that is done, then of course the last one is chosen. So that's 6 total, 3 times 2 times 1. Okay, so about our favorite. So figure 2, don't worry about the terminology of type 1 and type 2 and so on. I don't think you really need that. Okay, so on page 1031, but the reason why this is our favorite is if you have z as a function of x and y, then you have a lower function and an upper function. So your picture does not look like a box. Our favorite, which is just constants. Okay. But z is from a lower surface to an upper surface. Okay, and then once you get down to an xy plane, then let's say y goes from one function to another function, and then x goes from a constant to a constant, right? And there are variations on the theme. You can look at this, and you can look at this or not. Okay, but you're going to have some combination, right, of dz, dy, dx. That's our favorite, but it doesn't have to be that again. You can have dz, dx, dy, and so forth. Okay. Rules of the game, as you might imagine, as we said before. Took a look on some of the homework problems. I can get this focus, page 1037. All right, so take a look at, say, number 3. It goes dx, dy, dz. So the inside is x. That means the limits for x are allowed to have y and z. You're allowed to have the other 2 letters. So you can see here you have y minus x, y minus z, I guess, is x. Then once you get to y, notice y goes from 0 to z squared. Okay, but then z goes from a constant to a constant. Okay, so the inside integral, innermost, can have the other 2 letters. So for number 3, it says dx. You're allowed to have stuff that says y and z. Then you work your way back out. The middle one can only have the letter z, and then the outside is always constant. So if you look at any of these, the outermost is always constant. The innermost is allowed to have 1 variable, the outermost, and the innermost can have 2 variables. So dx can have y and z, dz can have x and y, dy can have x and z, or not. I mean, you don't have to have it, but you're allowed to have that. Okay, so for instance, number 5, dy comes first, so the innermost integral can have x and z. And then dx is allowed to have z, and you notice it's from 0 to 2z, but the outside integral always must be constants. Look at 3, 4, 5, 6. So any of those, the outside can only have constants involved. All right? And that's a basic principle. And something we've said before, that when you integrate, on page 1034, volume is the integral of 1 dv. V of E, volume of a box or a region, is a triple integral of 1 dv. Okay, so again, for length, integral of 1 dx or dx from a to b is just the length of the interval. Okay, so double integral dA is area, triple integral dV gives you the volume. Okay, so that's what we got here. Again, a lot of these could get really, really long. So, use whatever shortcuts you can for this. Okay, so on page 1037, I'll show you the homework problems again for those of you who don't have the book and aren't planning to get it. Hopefully that's somewhat readable. So there, and there. And then a few more on 1038, I guess it was. I think that's about it. All right. So here we go. So number 1, to tell us to integrate dy, dz, dx for the example problem. Okay. So they didn't give me this. So the original problem just said 0, 1, 0, 3, -1, 2. You work your way out. Okay. So in other words, these are the limits for y, then these are for z. Let me get this focused. And then this one is for x. Okay, so you integrate with respect to y first, which means x and z are constant. So that's x, y squared over 2, z squared, and y goes from -1 to 2. So take out the half. X, z squared is considered constant. Plug in 2, you get 4. Plug in 1, you get 1. So 1/2 of 4 minus 1, that's a constant, it comes out. And now we have x z squared dz dx. Okay, and 0 to 3 is for z, 0 to 1 is for x. So integrate with respect to z, x z cubed over 3. From 0 to 3, plug in 0, you get 0. Again, don't bother plugging in 0. We've got some integrals that are going to be so long, you'd rather not even fool with it. Plug in 3, you get 3 cubed is 27 divided by 3 is 9. Take out the 9. So I have 3 times 9 over 2. Integral from 0 to 1 of x dx. 27 over 2, x squared over 2 from 0 to 1. Plug in 0, you get 0. Plug in 1, you get 1. 27 over 4. And that is the same answer that you got in the example that they gave you. Okay, that's a basic idea of how these work. Set you up with number 3, but I wasn't going to do the whole thing. Okay, 2x minus y dx dy dz. 0 to y minus z. Notice x can have y and z. Then y is allowed to have z, but z can only have constants. Okay. All right, so integrate 2x minus y with respect to x. That's x squared minus xy. X goes from 0 to y minus z. Plug in 0, you get 0, so forget about it. Plug in y minus z, a little bit clumsy. Y minus z squared minus y minus z times y. So clean that up. That's y squared minus 2yz plus z squared minus y squared plus yz. Y squareds cancel out. Okay, and negative 2yz plus yz gives you a yz. So you're going to integrate z squared minus yz. That should be a yz there. Yz dy dz. Okay. So I just wanted to set you up with that one. That should be a yz. And just say, etc. You finish the rest of that problem. There's still a lot more work to do, but that's the setup for number 3. Okay. Number 5. And notice even when you plug in 0, some of them get long. So we're really happy to have the zeros, because if you don't have the zeros, problems get even longer. Okay, number 5. Sorry, I messed up. X e to negative y dy dx dz. Okay, integrate with respect to y, it's negative x e to negative y. I took a negative out. Plug in from 0 to ln x. Okay, so if I plug in ln x for y, I get x e to negative ln x minus x e to the 0. That's 1. Okay, and a little bit of timeout here. X minus e to the negative ln x, that negative 1 can climb up here as an exponent. E to the ln x minus 1. That way the e and an ln can cancel out. So I have x times 1 over x, which is 1. Very nice. So it just becomes 1 minus x. And now it's a nice, easier integral. And I decided to distribute a negative here. Negative 1 minus x is x minus 1. Okay, so that's going to be x squared over 2 minus x. X squared over 2 minus x. From x goes from 0 to 2z. Plug in 0, you get 0. Plug in 2z. 2z squared is 4z squared times a half minus 2z. So that comes out to be 2z squared minus 2z dz. Okay, so 2z cubed over 3 minus z squared. Plug in 2, I get 16 over 3 minus 4, minus plug in 1, 2/3 minus 1. Clean it up, 14/3 minus 3, 5/3. All right, number 9, they give me this information, triple integral over the region E of y dv. Okay, and they tell me this, this, and this. Now, based on that information and what we said earlier, can you tell me what has to be the order? You can't just throw down, y, z, x, or z, x, y, or whatever you want. The hint is that these are constants. This has one letter. This has two letters. Two letters has to be in the inside, right? So it must be dz because I see two letters, x and y. And then it has to be y because y has an x. And then this is the outside because those are constants. Now, if everything was constant, it doesn't matter by Fubini's theorem. So let's say this was 0 to 3, that was negative 1 to 4, and that was pi to e or whatever. They're all constants. So by Fubini's theorem, you can pick any order that you want. But since this has two variables that must be on the inside, dz, right? X minus y, x plus y. And then this one has a single variable. So dy has to be next from 0 to x, and then x from 0 to 3. Okay. So if I'm integrating y dz, that's a constant. So it's just y times the length of the interval, x plus y minus parentheses x minus y. That says length of the interval. And that comes out to be just 2y because x cancels out. Y minus a minus y is 2y. So you're integrating 2y squared dy dx. So it's 2y cubed over 3 from 0 to x. Plug in 0, you get 0. Plug in x, you have 2/3 x cubed. And that should be pretty straightforward. So 2/3 x to the 4th over 4. Plug in 0, you get 0. Plug in 3, you have 1/6. Let's see, 2/3 times 1/4 is 2 over 12 over 1/6 times 3 to the 4th is 81. Final answer is 27 over 2. Okay, 13, triple integral over the region E of 6xy dv. Okay, going from the xy plane to z equals 1 plus x plus y, bounded by y equals radical x and y equals 0, which is the x-axis, and x equals 1. So in the xy plane, it looks like this, and you're bounded by the xy plane and z equals 1 plus x plus y. So it is our favorite. Okay, dz, dy, dx. Z goes from the xy plane, which is z equals 0 to 1 plus x plus y. Y goes from 0 to radical x. X goes from 0 to 1. Okay, again, 6xy is constant as far as z is concerned. So it's just a constant 6xy times the so-called length of the interval, which is 1 plus x plus y minus nothing. Okay, distributes. I take out the 6. Xy plus x squared y plus xy squared dy dx. Okay, so integrate with respect to y. Xy squared over 2 plus x squared y squared over 2 plus xy cubed over 3 from 0 to radical x. Plug in 0, you get 0. Plug in radical x, you get x times radical x squared is x, and 6 divided by 2 is 3. Okay, plug in radical x here, you get x squared times x, and then 6 divided by 2 is 3. And this gives me radical x cubed, which is x radical x, times 6 divided by 3 is 2x. So that comes out to be 3x squared plus 3x cubed plus 2x times radical x is x to the 5 halves. All right, so x cubed plus 3x to the 4th over 4 plus 2 times x to the 7 halves times 2 sevenths. Plug in 0, you get 0. Plug in 1. 1 plus 3 fourths plus 4 sevenths. 65 over 28. Okay, I decided to skip 15 because it turns out to be long. I mean, it's doable, but it's just really long, so I decided to skip it just to show you what it's about. It's a nice problem, but you end up integrating a mess like this, and it just got too long, so I said, forget it. Okay, 17, triple integral of x dv bounded by x equals 4y squared plus 4z squared and x equals 4. So x is a function of y and z, as it were. Okay. And to find out where they intersect, 4 equals 4y squared plus 4z squared. That means y squared plus z squared equals 1, a unit circle in the yz plane. Okay, so we have z equals 4, z equals 4x squared plus 4y squared. This is above, this is below. So by analogy, this is below, this is above. So I switch the polar coordinates. So I'm integrating x dv. So dv is dx r dr d theta. X is going from 4 r squared, where y squared plus z squared is r squared, to 4. Unit circle means r goes from 0 to 1, theta goes from 0 to 2 pi. Okay, you can see this thing, I messed up real bad here, but this thing doesn't depend on theta, so take out the length of the theta integral, which is 2 pi. Okay, so I have r here, integrated with respect to x is simple, x squared over 2, and you're going from 4r squared to 4, then I have dr. So let's see, that 2 cancels that 2, pi is outside, I have an r, plug in 4, you have 16, plug in 4r squared, I have 16 r to the 4th. Okay, take out the 16 pi, and then I have, let's see, r minus r to the 5th. So 16 pi, r squared minus r to the 6th over 6 from 0 to 1, which is 16 pi, plug in 0, you get 0, plug in 1, 1/2 minus 1/6. That's 16 pi times 1/3, 16 pi over 3. Okay, then finally 19 says 2x plus y plus z equals 4. They give it to you like that, but you want to solve for z. Z equals 4 minus y minus 2x. Okay, draw myself the picture. So I found the x, y, and z intercepts, 2, 0, 0, 0, 4, 0, 0, 0, 4. So it looks like this. And in the xy plane, 2, 0, 0, make it 2, 0. 0, 4, 0, make it 0, 4. Comes out to be y equals 4 minus 2x. Slope can be easily found to be -2. Y intercept is 4. Okay, so z is going from 0 to 4 minus y minus 2x. Y is going from 0 to 4 minus 2x. X is going from 0 to 2. dz, dy, dx, which is dv. All right, and so you're integrating 1, so it's just the length of the interval, 4 minus y minus 2x. Integrate with respect to y. 4y minus y squared over 2 minus 2xy. Plug in 0, you get 0. Plug in 4 minus 2x. I messed up real bad. So 4 times y, which is 4 minus 2x, minus 4 minus 2x squared over 2 minus 2x times y, 4 minus 2x. You can see this gets real clumsy. So distribute 16 minus 8x minus, okay, so I squared this as 4x squared minus 16x plus 16 divided by 2 minus 8 plus 4x squared, which is 16 minus 8x. And then I distribute this minus 2x squared plus 8x minus 8. Leave that alone. Let's see, then what happened? 8x and minus 8x cancels out. And I combine -2x squared and 4x squared, giving me 2x squared minus 8x. And then 16 minus 8 is 8. Okay, so 2x cubed over 3 minus 4x squared plus 8x from 0 to 2. Plug in 0, you get 0. Plug in 2. 16 over 3 minus 16 plus 16 cancels out. Final answer is just 16 over 3. All right, so that was section 15.6 on triple integrals.